bending moment and shear force diagram in multi-force member. But before that, we will give some introduction about the, and we will also see how to classify truss and these beams under the two force and multi-force. Second point is that how to find out the internal forces in truss as well as in beam, how they are completely different, and then we will start the procedure for drawing the bending moment diagram and the shear force diagram. So let us start with first of all the difference between number member and multi-force member. Two force member, the characteristic of this particular point is that it is acted upon by both the forces are equal and opposite. And the third point is that both of them have same line of action. So there are certain examples in which you will be having. So examples include a member acted upon by a force, let's say F here and F here. No, so here since they are acting at these 2 points and they are equal to each other and they are also opposite, and the third point is that they have the same line of action, hence this one is a two force member. Now another example that you can get is when you have two forces which are acting in this direction, this is F and also here. So in this case also you can see that the two forces which are acting at 2 points are same, they are opposite to each other, and the line of action for these two forces are also same. So this qualifies for the two force member. Now in a similar way, how to define multi-force member? When a member acted upon by at least one transverse load. So under that condition it will qualify for your multi-force member. For example, and obviously the number of loads over here will be more than 2. Okay, so this is one point. Second point that qualifies is the number of points where forces are acting are more than n. And third point is if all these conditions opposite to the condition of Now example for multi-force member include, for example, simplest example is have a wheel supported over here, acted upon by a concentrated load F. So if you take this member, if you draw the free body diagram of this particular member, have one load here, another load. Here you will have RAX, here you will have RAY, and here you will have Y and F. So certainly this qualifies for multi-force member, but in relation to this, you will see that for having transverse loads which are acting over there. Alright. So this is one very good example. Another example for multi-force member can be for having like and the force which is acting in this. So this is also called multi-force member. Okay, so this is all about the concept of two-force member and multi-force members. If we try to see here, force member example here. So trusses, the truss members which can take axial forces like tension or compression, they belongs to the category of two-force member, and beams which is acted upon by the vertical loads, they also have reactions at the fixed point, so they belongs to the multi-force member category. So example here is and frames. The frames also contains at least one multi-force member, and we will talk about all these in the. Now, after finding out, after characterizing the two-force member and three-force member, what we have to do is we have to find out how the internal forces exist in these forces. So let us try to talk about internal forces in two forces. Internal forces. So first of all, internal force in two-force member. So in two-force member, internal forces will be either here, internal force either tension or compression, or one can write down these forces are mostly axial forces. For example, let us say if you have certain member which is acted upon by equal and opposite forces, or let us say P instead of P, let us say the load is P. So if we have to find out the internal force in, first of all, what kind of member is this? This is a two-force member. So if we have to find out the internal forces here, we will cut a section. Let us say section AB. Now if we take, and this is AB section, and let us, if we take this portion as X, so if we have to draw the free cuboid diagram of this section up to this x, what will happen? Here you will have P, here you will have axial force. So this is your internal force F. But when you write the equilibrium equation Fx is equal to 0, what you will get? So two force members always has internal forces which are axial in nature. Now let us talk about multi-force member. In multi-force members, the example includes somewhat like, let us say, here you are having P1, having load P2, you have P5. Okay, so obviously this seems to be a multi-force member because it is acted upon by many forces at different points and also it has transverse load. Now if you have to find out the internal forces anywhere in this particular set, then how the internal forces will act? AB at this time from and section X from the end. So if we have to replace internal forces over here for this member, X, so in this case you will be having internal forces. First of all, there will be axial load F. Okay. Then there will be some kind of shear because you are having transverse load. It will try to shear the object. So in this direction, you will also be having load in the vertical direction. Then, since these loads are not passing through the same point, so it will also have a bending effect. That the internal forces in multi-force member consist of three types of forces in any section, and they are F is your axial, and M is your so therefore it is required that how, so you can see the difference here. Here you had just one axial force, so here F is your axial. So in terms of internal forces, two force members contain just axial internal force. However, multi-force member contains three types of internal forces or movement. This one is your axial, which will be along the axial direction. Second one is your shear force. Third one is your bending movement. And this is what basically is the very universal kind of internal forces that you can consider in any kind of that you are. So let us try to understand how the shear force and bending moment acts in multi-force member, and we will try to demonstrate the variation of this shear force and bending moment by taking an example of a wheel. Okay. So now we now know that how the shear force and bending moment arise in the multi-force member. So let us see how it varies for a given multi-force component. Talk about bending moment and shear force. So in this case, first of all, what is the sign convention? We just now saw that any multi-force member that you are going to take, there you will have one axial load and shear force and bending moment. Okay. Add load in this direction, we had load in this direction. This is your Ry and this is your Rx. So for a given section, so at a given section over here for a material, this is how we try to find out the bending moment, shear force and axial force. Now the thing is how to use the sign convention for this. So first of all, let us try to add the positive sign convention for, first of all, shear force. So if a body is trying to shear off in the direction of clockwise, then we consider that as a positive shear. For example, let us say if you are having this structure and you are taking section about this. Now, if shear force has to be taken as positive if it is trying to shear in this direction, that here it will be down and here it will be positive sign. In other words, if you just try to see, take a section like this, there is a section that you are taking. The positive sign for the shear force will be again in a similar way. If you go in this direction, this will go in this way. If you go from this direction, this will go in this way. And V will be positive when it tries to shear the material in clockwise direction. What is the positive sign convention for shear force? Similarly, the positive sign convention for bending moment can be obtained when it tries to bend the whole structure in upward direction. Okay, it means that if for a given section or member, if your bending moment is actually such that it bends upward, it means that it tries to bend this way. To bend this particular element in this direction, how you will have to apply the moment? You will have to apply moment in this direction, right? So this is what is your positive moment convention. If you take it in the direction, moment. Okay, so when it is positive, this is what we take. Similarly, if you take it in other way round, for example, the same thing if you want to write negative, and here it will become like this. Okay, so V. So basically, if you want to take combined structure in which we are having shear force which is positive, bending moment which is positive, here shear force positive, bending moment positive. So this is positive sign convention. Here V M but some element, let's say ds. How we try to take the sign conventions. Now what is missing is axial one. So whenever axial is under tension, let's say F, so this is again considered as a positive. Okay, so the sign convention for axial force, shear force and bending moment can be considered like this. Now if we are starting from this direction, So this is what will form the positive direction for V, M and F. If you are taking section from this direction, it means that this will form the axial is in this direction, shear force in this, moment is in this direction, form the positive, well, like sign convention for all these points. Okay. Let us try to apply example. So let us take which is acted upon by distributed load W. Formally distributed load W. Let us say this W is called Newton per unit length. Okay. So this is load intensity W acting, and this beam is supported by, here you have simply supported and here you have roller support. This one is fixed like this. Now let us take from this, let's fix our axis over here, Y, and this is your X. Now we have to find out the bending moment and shear force diagram. So first of all, subjected to these loadings, you have to take a section this and section this. So this is A and this is A and this is B. So we are going to take section dx from A to B. So how it really? The section on which you are having the distributed load. Here this length is given as, okay. Now how you will replace the internal forces on this side and this side? So again, first of all, since you are going from this direction, so what we will do? We will take here the shear force will be, since there is no axial external force, so axial component will be 0. So we will just take shear force and bending. So this is your V, and let us take this as M. Over a distance dx, there will be change in V and M, and let us take V and moment as M plus V. Okay. And this point is your A, this point is your. Now let us write down the equilibrium equation for this point. So summation of Fy equals to 0. What it will be? Summation of Fy will give you minus V minus dV plus V minus W into 0. So this will give you y dx is equals to W minus 7. So the relationship between the load intensity that you have applied and the shear force. Now if you want to know the variation of V over the given load, how so? Over, let's say, when x varying from 0 to L, so what will be your total shear force? Minus W into dx. That shear force is nothing but area under the load intensity curve, but with the negative sign. What you have to be clear with is, you have to divide this particular limit, integration limit, from one region to another where the load intensity is constant. When load intensity changes, you will have to Okay. Similarly, we can take the moment about B. Moment about B at this point, you can, what you will be getting? First of all, this one is giving minus m, and V times dx. This is again V times dx, which is minus. This is plus m plus dm, and w into dx and dx by 2. W into dx by 2 dx by 2. Now taking the, so here these two will get cancelled, and taking the order of term x and neglecting this even smaller term, which is dx. So what you will get, this will get cancelled. Okay. So ultimately you will be getting here dm by dx, right? So you can see that the variation of bending moment is nothing but equals to the shear force. But what is shear? If we try to write down this particular thing in terms of your load intensity, that we can differentiate it twice. So dm by dx square from dv by dx, and is nothing but minus w. That bending moment can also be correlated with the load w. Okay. There is another case over here. If you differentiate it over the whole length, what will happen? So dm is equals to nothing but v into dx. It means that total m is nothing but area under the shear force diagram. Area under the shear force diagram by v. So moment. So we can see the relationship between different quantities here. There is one relation which is m and v. There is another relation which is between m and v. These are important relationship where the load is related with the shear force and bending moment. Alright. So this is what the basic concept of your bending moment and shear force. Let us try to draw bending moment and shear force diagram for a given structure. Example. So let's take one structure which is here the load P is applied. Let's take, or is fine. We can take the load P is applied in this direction, and we are having support like this. First thing that you have to do is you will have to find the reactions. So what will be the free body diagram of this particular body diagram will be? Let us say this is A and B. Here have R A Y. Here you will have R A X. Here you will be having R B Y, and here. Now, we have equation. summation of fx is equal to 0. That will give you rax is equal to 0. Summation of fy equals to 0 will give you ray plus ry is equals to e, and moment about, let's say, a equals to 0. Let us say its total is your L, and this one is L by 2, and this is also L by 2. Okay. So in this case, this is your L by 2. L. So summation of MA equals to 0 will be given by E minus P into L by 2 plus RBY into L equals to 0, and this will lead to, and using this particular equation, RAY, so we found RAX is equal to 0, RAY is equal to P by 2, RBY is equal to 2. So using this particular relationship, after finding out these reactions, we have to now draw the shear force and bending moment diagram. So how to find out shear force and bending moment? First of all, we have to find out the point where the loads are changing. First of all, start with, so again drawing the same thing. So here you are having P by 2, here also you are having P by 2, here you are having, total is your L, and this one is your 2, this one is your L. Okay. So first of all, if you start from here, let us also fix your y and x. When you start from this direction, so your load is is constant. Here it is changing. However, when you start from here, non-zero x, it goes up to this point and then it changes. It means that the number of sections required to draw the shear force and bending moment diagram depends on where is a change of forces happening. It means that there is a change. So change of load happening or occurring in x, or x belongs to L by 2, and then from L by 2 to L. So after defining this section, you will have to take two sections in this. So in this portion you have load constant, which is nothing but your P by 2, P by 2. And in another section again you will have load constant, is in the opposite direction of P by 2. However, you can see that from here when we come, again this comes up, it means that we have to take another section. So after defining or finding out this change in load, this implies that we require two sections. Okay, we require two sections, and under this condition by 2 sections, and under this condition we can just try to solve the problem. So let us say pick a section here which is AB and section here section more and time which is the positive. Write down those that what will happen, and summation of m about b equals to 0 and negative x, and let's say this distance is at x which is equal to x. Okay, so for one section what you are really getting here, the relationship is for x L by 2, you are having your shear force which is P by 2. Mind that there it is positive and bending moment is given by P by 2. Now let us try to find the same thing about this section. So now section, again second part only, is section CD. So in this case, when you take the section, here it will be and we are taking here x, here P load is applied, we will have P by 2, here force is E, M, and again writing y equals to 0 will leads to by 2 minus v equals to 0. It means that summation of md equals to 0 will lead to what? That will lead to m plus x minus L by 2. So if you try to write down this particular point, x, okay, x plus PL by 2 means that you are going to get things like P by 2, L by 2, 1 minus. Okay. It means that for the section x, L by 2 to L, your shear force is L by 2, 1 minus x. Okay. So this is how you try to find out shear force and bending moment as a function of x in this section, and let us try to draw the shear force. So the shear force diagram, let us say between this region, shear force diagram is says that P is positive, so it is positive here, which is this particular thing is P by 2. When it goes into another section, it becomes minus P by 2. So it will jump to minus P by 2 and it will become. How your shear force diagram looks like. So here it is positive, here it is negative. sent over here. So now, what about bending moment diagram? Bending moment. So bending moment in this section is linearly varying, and its value becomes PL by 2. Here it is 0, its value becomes PL by 2. So this, right? Now, in the little stage, what is really happening? When x is equal to L by 2, sorry, x by L. When x is equal to L by 2, what will happen is here it is PL by 2. When x is equal to L by 2, so this is what will make sense. I made some mistake over here. The calculation, however, I like what you will be getting is then. So if you draw this particular diagram over here, what will happen? We will have m is equals to, so x is equal to L by 2 will give you 1 minus 1, x is equal to L by 2 something like, so what we will do is we will just try to again like get that relationship of m so that we don't really get it. So the section that we got over here was m, right? It was p, it was L by 2, x, this one was p by 2, right? Summation of m at this plus p x minus L by 2. Okay, and this will be, okay. So you can see here, and this will be equals to 0. M comes out to be p by x. Here it is minus px, and there it is plus pl by 2. That minus p by 2x, here pl by 2. L minus x. Okay, so this one is the correct formula. So let me clarify this one. So this m will be given by p by 2 L minus x. Okay. So when you have to find your p from here, so at x is equal to L by 2, you will be getting L by 4. Okay, PL by 4. However, when you substitute here, start from here. But when x is equal to L, this will become 0. So this is how you will have to draw your shear force and bending moment diagram. And this is the end of this.